In this video, we're going to be taking a look at giant covalent structures. And giant covalent structures are basically structures which are composed of a network of covalently bonded atoms. Now, there's another name which is sometimes used to describe giant covalent structures, and this word used to describe it is macromolecular. Macromolecular. So sometimes giant covalent structures are described as being macromolecular structures, and this just means that it's this is referring to the fact that these structures contain many millions of atoms usually, hence the word macro, which means big or many. It's a large scale, which is referring to the idea that it's large scale in comparison to molecules, which are usually like small. Now, in this video, I'm going to be talking about two important macromolecular structures. I'm going to be talking about graphite, and I'm going to be talking about diamond. So first of all, I'm going to be talking about graphite. So here I have a sheet of graphite here, and this is just a small section of what graphite is basically composed of. This is just a tiny section of it. Usually this would spread out in all these different directions, and as you can see, we have layers here. I'll talk about the layers soon, but anyway, as you can see here, we have these black dots and we have these gray lines, and these black dots in this particular diagram represent carbon atoms. Carbon atoms, and these gray lines in the structure represent covalent bonds. And these covalent bonds are quite strong, so each of these sheets of graphite are quite strongly bonded, like the carbon atoms in it are quite strongly bonded. So as you can see here, the carbon atoms are bonded through covalent bonds, and each of these carbon atoms has 3 covalent bonds linking to other carbon atoms. Now, carbon has the electronic configuration of 2,4 if you're looking at the inner electron shells and the outer electron shells. So you'd expect usually carbon would form like four bonds, whereas in here you can see, as you can see, these carbons have only formed 3 bonds. Now the reason for this is because the fourth electron is delocalized, and this means that the electron basically is able to float. It's basically able to float around between these different atoms, and basically all of these atoms are sharing them. And the way this works is that each of these atoms donates its outermost electron, its 4th electron in the outer shell, and so 1 electron per atom is delocalized. Now what this delocalization does is increase the strength of these sheets, and not only that, it allows electrical conductivity. Now if we take a look at the sheets, the way the sheets are arranged, this is a small diagram of how the sheets would be arranged. And if you look at this, one thing you might notice is that the lengths of the bonds between these the length of the covalent bonds between these carbon atoms here are quite short compared to the length, the distance between the carbon atoms in different sheets. And the reason for this is because between the sheets, obviously, there are no covalent bonds, and so they're not held closely together tightly by covalent bonds. Now, what is acting between these layers is a type of intermolecular force, and this kind of force is known by the name of van der Waals forces. And this is a type of really common intermolecular force, van der Waals forces. Van der Waals forces. And I will be making a video about van der Waals forces when I'm talking about the different kinds of intermolecular forces. Now, graphite, because of these weak bonds or weak forces between these sheets of graphite, what happens is these sheets can actually slide over each other. So imagine this one could actually slide over the top one, So this one might slide that way, and this one might slide that way. So they can easily slide over one another, each of these layers. And because of this sliding, the fact that they can slide over each other, graphite is a structure which is used as a lubricant. It can be used as a form of a lubricant, which is a dry lubricant. A dry lubricant. And this is quite useful because in some areas of like lubricant application, we wouldn't really want a lubricant which isn't dry. Like, for example, if you have a zip on your jacket or something, so zips, and if you have a zip, you might want to have you might want the zip to be able to go up the you might want it to be able to zip up quite easily. So we'd want a dry lubricant because, you know, a lubricant which isn't dry is going to be a bit inconvenient. And it can also be used in things like keyholes as well. So this is what one of those things we'd use it for. And another property, another use for this property is pencils. We can actually use this we actually use graphite in pencils, and the reason for this is because as we write with our pencil, so imagine I'm writing with a pencil here. As we write with our pencil, pieces layers of the graphite are rubbed off and they stick to the paper as we run our pencil along the paper. And so this is one of the applications of graphite. And now if we go back to this idea of the strong covalent bonding, these covalent bonds are quite difficult to overcome, and because of this, the melting point of graphite is very, very high. Because of these really strong covalent bonds, they would have to be overcome in order to melt this giant covalent structure and overcome and break the covalent bonds basically. And what graphite does is, it's a bit strange. It doesn't actually form a liquid. What it does is it goes straight from solid. Oh wait, I'm still on pencil. Anyway, it goes straight from solid to a gas. And this process of going from a solid to a gas is this is a transitional phase, and the transitional the state transition that is occurring here we describe with the word sublimation. So obviously you have solid to liquid, which is melting. You have liquid to gas, which is boiling. And in this case we have another state transition, which is solid to gas, which is sublimation. So we describe this as the solid has sublimed into a gas. So like you'd say it's melted into a liquid, or boiled from a liquid to a gas. In this case it's sublimed from a solid to a gas. And this is one of those properties which happens not only with graphite, but it also happens with diamond, which I'm going to be talking about very soon. So because of this, the melting point, not because of this, but because of those strong covalent bonds, the melting point of graphite is very, very high. And the sublimation process which happens, happens at over 3,900 Kelvin. And 1 Kelvin is like 1 degree centigrade, but no, it's like minus 273 degrees centigrade. So this is like, this temperature which we can see here is somewhere around I don't know, like 3,500 degrees or something. So anyway, so it's got a high melting point. And apart from this, if we take a look at the idea of delocalized electrons, so delocalized electrons, right? This substance has a lot of well, because of the delocalized electrons, as I said before, it conducts electricity. So it has a good electrical conductivity because of these electrons, because these delocalized electrons are free to move, and so they allow the current to flow through these layers. And what usually happens is that the current flows along the layers, so along these layers, but it doesn't really flow between them. It flows along them, but not between them. But in a typical graphite, like if you've tried passing a current through a pencil, you might notice that it actually conducts, even though most of the time pencils are contain lots of different shaped graphite crystals which are pushed together. And so what might happen is that this sheet, one of these sheets of graphite, might be touching. Hold on, let me get this. There we go. One of these sheets of graphite might be touching another sheet of graphite, and so the current might be able to flow through this one and to that one, and then it'll somehow, the electrons will find their way. They'll find a path to get to the other side, so they can still conduct. But usually it passes just through the sheets, along the sheets. So it conducts electricity. And now let's take a look at another thing which can be affected by the fact that these covalent bonds are really strong, and that is solubility. Its ability to dissolve in a solvent. Now graphite, in order for graphite to dissolve in a solvent, what needs to happen is that these covalent bonds, which we can see here, these covalent bonds need to be broken. And in order for a solvent to break those covalent bonds, it's going to need to exert a very, very strong force on these atoms to pull them apart. And pretty much all solvents don't do that. And so graphite is insoluble. It's insoluble. It basically does not dissolve. It does not dissolve because of the fact that these covalent bonds would need to be broken, and they're really strong, so they don't get broken. Okay, so those are the properties of graphite. And because of the fact that graphite is has quite a long distance between these layers, what happens is this can actually be used in tennis rackets. And if you look down, I've got a picture down here of a tennis racket, and this tennis racket is made of carbon fiber, and one of the components of carbon fiber is graphite, and it's used because of its low density. So you've got a lightweight tennis racket which you can use to hit a tennis ball, and so this doesn't provide too much weight on your hand. Now if I now take a look, let's now take a look at diamond. And you may be familiar with diamonds, probably, like, you know, these shiny things. Anyway, so this is the molecular sort of structure of diamond. And again, just like the graphite sheet I showed you, this is just a really small section of what it's a small section of what actually exists in a diamond. So this would spread out in all different directions. Now looking at these atoms in diamond, what we notice is that each of the carbon atoms, so this is one of the typical carbon atoms which exist in graphite, each of the carbon atoms is bonded covalently by strong covalent bonds to four other carbon atoms. So 1, 2, 3, 4. And if you're familiar with the molecular shape of methane, you would notice that methane has 4 bonds as well to other hydrogen. In that case, it's carbon to hydrogen, but in here, what we have is carbon to carbon, and this shape here is actually a tetrahedral shape. And this is because if we were to join these atoms, these bonding atoms together, we would basically be constructing a square, a triangular based pyramid, which also goes by the name of tetrahedron, as you can see. Now, because of the fact that we've got these strong covalent bonds, and if we look at the structure of the electronic structure of carbon 2, 4, all four of these outer electrons of carbon are occupied. They're basically bonded to these other carbon atoms, so none of them are free to move. And because none of them are free to move, one of the properties of diamond is that it does not conduct electricity. It does not conduct electricity because the electrons are tightly bound in these localized covalent bonds. Now, another property of another property of diamond is that just like graphite, because of these really strong covalent bonds, it does not dissolve very easily in any solvent. So it does not dissolve in pretty much any solvent. And because of this, we say that it's insoluble, since these covalent bonds would need to be broken for it to dissolve, and then they don't get broken in solvents. And one of the other features of these covalent bonds is that since they provide such a really they make diamond a really hard substance, it's very useful because what we can do is we can use it to tip drills. Like this drill basically has fragments of diamond on its tip, so it's basically a diamond tip drill. And these fragments of diamond basically strengthen the tip, so it's able to get through really tough materials that it wouldn't usually be able to get through. And also here we've got a diamond tip saw, so if you look carefully at the rim, the tip of this saw, it's got fragments of diamond on it, and that makes it really strong, so it's able to get through a lot of different materials. So it's not only insoluble, but it's very hard. It's insoluble, it's hard, does not conduct electricity. And now let's look at something else. And that thing I want to look at is the melting point. As I said before, diamond is something which actually sublimes. It doesn't go from solid to liquid to gas. It goes straight from a solid to gas. It just skips the liquid phase. So it goes from solid to gas. And it does this at a very high temperature. So the main point here that I want to make is that it has a very high melting point. Very high melting point. And the melting point of this diamond is around 3,800 Kelvin. 3,800 Kelvin. And you may notice that 3,800 Kelvin is actually lower than the melting point of graphite. And the reason for this, which I'll explain, is that if we take a look now up here at the structure of graphite, we have a couple of things which resist the breaking up of this structure. The first thing is the free covalent bonds. And looking back at diamond quickly before I go on to further talk about this, looking back at diamond, you might notice that diamond has 4 covalent bonds, whereas graphite has only 3 covalent bonds. So you might be wondering, wait a second, diamond has more covalent bonds than graphite, so why doesn't it have a higher melting point? Well, the thing is, despite the fact that diamond has 4 covalent bonds, graphite has not only 3 covalent bonds, but it has delocalized electrons. Delocalized electrons. And if you're familiar with the structure of a molecule known as benzene, benzene is a very stable cyclic molecule, and the reason for this is because it has delocalized electrons, and this also has delocalized electrons, graphite. And because of those delocalized electrons, the structure is very stable. So not only is there a bond like between here and here, and here and here, and here and here, but there's also a sort of shared attractive force between them, caused by the free flowing electrons, and this increases the strength and stability of it. and causes the, and this is the reason why the melting point is slightly higher than the melting point of diamond, even though diamond is a really hard material. So yeah, electricity, insoluble, hard, solid to gas, very high melting point. I think that's about it. Yeah, that's about it. So I hope you guys found this video helpful, and I'll see you in the next video.